So let's continue with this chapter, just introducing us to some of the behavior of light. So the things that we talked about last video were the ways that we can describe light, and then we also talked about reflection and refraction. In this video, we're going to look at total internal reflection and also dispersion. So just to remind you, reflection is when light hits a boundary between two materials and reflects back. Refraction is when the light goes from one material into another material and it bends at that boundary. We learned that the law of reflection is that the angle that the light comes in at is equal to the light that it reflects at. We learned that the law of refraction is governed by what we call Snell's law, that has to do with the index of refraction and the angles. The index of refraction is a ratio of the speed of light in a vacuum to the speed of the light in the new material. So the slower the light goes in that material, the greater the index of refraction will be. As light will go into a slower material, it will actually bend towards the normal. If light goes from a slower material to a faster material, it bends away from the normal. Another really cool thing that happens with light is this thing called total internal reflection. I like to use these swimming pictures because you see it a lot, where you can see both the person, the front, and also the reflection of their back off of the bottom of the off of the surface of the water. There was also a picture in your textbook about a guy looking at a goldfish tank, and he could show you two images of the fish. That also has to do with total internal reflection. So what is it? Well, basically, if we remember the the Snell's law, n1 sine theta 1 equals n2 sine theta 2. Now, total internal reflection is always going to happen when you go from a material of higher n into a material with a lower n. That means when it goes in from a material where the light is traveling slower to where it will speed up. So basically, in this picture, they have a nice illustration of light hitting the boundary between water and air at different angles, and you can see the light is refracted and it bends away from the normal. As the angle of incidence increases, so does the angle of refraction. But notice, and if you think about it, this angle is getting closer to the boundary between the two surfaces. There's a point at which, instead of passing into the air, it actually will reflect off the surface. And this is what we call total internal reflection. Here's something a little bit more, not as much of a picture, but more of a diagram. So here we have the incident light wave, and then we see it's refracted. Now, sort of the special situation is when the refracted wave at the boundary is 90 degrees, so it's just skimming the surface. The angle of incidence in this case is called the critical angle. If your angle of incidence is greater than your critical angle, you will have total internal reflection. The light will not pass into the new material. It'll stay in the first material. So the way that we figure out what is the critical angle, we would say n1 times the sine of the critical angle. Now, the critical angle is the angle at which the angle of refraction is 90 degrees. Of course, the sine of 90 is just 1, so the sine of the critical angle is equal to the ratio of the two indexes of refraction, which of course must be less than or equal to 1, because the sine can only go up to 1. And so this means that n2 must be smaller than n1 in order for us to have total internal reflection. Total internal reflection doesn't just make cool optical illusions or cool pictures, it's also used in fiber optics, where we send the information is in the form of electromagnetic radiation, a light ray, that enters the fiber optic cable, but it can actually go in crazy bendy paths, because if it hits the boundary between the fiber optic cable and the air at a large enough angle, it'll totally internally reflect and it will remain in the cable. And that way you can actually literally bend light. In order for this to happen, the index of refraction of the fiber optic has to be greater than that of the material that surrounds it. And to really ensure that, we can actually put some material that around the fiber optic cable that has even a lower index of refraction to make sure that nothing leaks out. Now, the last behavior that we're going to look at is called dispersion. And dispersion is basically has to do with the fact that the index of refraction for light is actually dependent on the wavelength. Sometimes the difference isn't a big deal, but sometimes it's noticeable that it actually causes a noticeable visual effect. So for these different materials, they have the index of refraction graphed as a function of visible light. Now if we get to the bottom, the fluorite is a relatively level line. So it means that the index of refraction does not vary a lot between the violet light and the red light. But if you look at the top and also the sort of the middle, you see that there's more of a curve, and there's a more significant difference in the index of refraction for violet light compared to red light. In general, the index of refraction is decreasing with increasing wavelength. So what does this do? Well, what happens is when light enters into this material where the dispersion is going to take place, the angles of refraction will actually be different, and so the light gets separated. And so what happens is it becomes easier to see the light of all the different wavelengths. And so in here, like, is, the Roy G. Biv, is all the different colors in between red and violet. When it happens once, sometimes it's not as noticeable, but the way that a prism works is that the light actually gets refracted twice, and so this separates the wavelengths even more, and that's why if light just comes in the form of white light, which is actually made up of all the different colors of light, it's all together, it refracts twice at the two boundaries of the prism. And so what comes out the other side is basically you can see the colors separated by their wavelength, and you can see the rainbow. This actually also happens in water droplets and is responsible for why we do see rainbows on a rainy day if the sun is out, because the sunlight comes into the water droplet and it actually will totally internally reflect, and it also is refracting as it passes out of the water droplet. And so this separates the wavelengths separates the light by their wavelengths, and you see the different colors. And so as an observer, what angle you're at is going to determine which wavelength you're going to see, and it also gives the rainbow its curved appearance. The secondary rainbow is caused by light rays that reflect twice inside of the water droplet before they come out. So that's all that we're going to do for this chapter. We're not going to cover polarization, but we're just going to kind of keep it at this, and then we're going to move on to understanding how some images are formed in the next chapter.